Hey everybody, it's Mr. Wolf. We're back with Unit 6. Finally away from Unit 5, but don't forget that stuff. That stuff's very important, and we'll relate it to what we're going to be going through on Unit 6 as well. But Unit 6 focuses around the idea of circles. I mean, everybody knows what a circle is, but when you ask the question, what is a circle, in a geometry class, you're often looking for an answer that's maybe a little bit more specific than just, a perfectly round shape. So let's talk a little bit about what we know. So we've dealt with polygons. That's not the tool I need. We've dealt with polygons before, and we know that polygons, they have, sides that are straight, no curves. Those are properties that you guys should be well familiar with. And they have different sets of properties depending on how many sides they have and how their sides interact with each other and whether they're parallel or and whatnot. And you guys covered that, but the circle is a very different thing. A circle is one. It's not made of segments. Not made of segments. So all you've learned this year, we've focused heavily on line segments and lines and angles, and now we're completely straying away from that for a short moment in this unit. But a circle is not made of segments, meaning it has no sides, no sides at all. I guess you could think of this outside of the circle there as just one big side, but that would not be the best way to think about it. Think of a circle as having no segments, no actual sides that you can label. The circle has a center point that is fixed in place and is in the direct middle of the circle. Oops, that's not how you spell middle. Okay, so the center point, and this is obviously not going to be perfect because I'm drawing by hand here, but we'll say that's the center point. And we can do a lot with this center point. One thing about that center point is that you can say that any distance or any point on the outside of a circle is equal distance from that center point. So let's write that out. Any point on a circle is equal in distance from the center point. For this case, we'll say C. We'll label it C, and we'll call this C. So from point C on this circle, any point you pick on the outside of this circle is going to be equal in distance to that center point from the other one. So whatever this distance is here, we'll call this X. And whatever this distance is here, we'll call this Y. We know for a fact that X will equal Y. Another bit of information here that's pretty important before we move further. Actually, we'll use this little circle that I accidentally drew up here at the top to do this. When it comes to notating a circle, you would notate it by its center point, and you'd write something like that. Let's clear actually a little space here. Let's clear a little space and draw this out. So this one, the circle over here, we'll say this is the center point, and we'll call it C for now. And we would call this circle C. And that's a very crude drawing. It doesn't have to be a perfect circle because, of course, you're not going to draw one. So, but you draw a circle with a dot in the center, and then whatever that center point is, and that's how you label the circle. So if you have a bunch of circles, we'll call this one D, and this one Y, and this one A. You could label these all as, well, this one right here would be circle A, and this one would be circle Y, and this one would be circle D. So this is very important so that we know what exactly you're talking about. Because if you just said, let's clear some of this out. If you just said we're talking about the circle C, but you didn't notate it, I'm going to think you're talking about this point in specific, not the circle. So keep that notation in mind. A circle with a little dot in the middle of it. So let's move on and talk about a very important bit of vocabulary, a very important part of circles that you guys will be using for a lot of things. And this is the radius. Radius. I know it's written there, but this is important. The radius of a circle is any line segment from the outside of the circle or on the circle to the center point. So all those little paths we were drawing on this last slide, the little dotted paths, those were line segments like the one we drew here. That is the radius. So we'll just label this one R. So R is the radius. And the radius is from the center point to the edge of the circle. From the center point to the edge of the circle. And as the size changes, let's say this, as size changes of the circle, the radius will change. And I know that makes sense and it seems obvious, but it's an important property to remember. The radius will change. So what we're saying here is that if you have a small circle, the radius is going to be smaller. If you have medium-sized circle, it's going to be in between that of this one and this one. So that radius is going to change in length as the circle changes. It's not a fixed number or anything like that. Something very similar to the radius that you guys need to know is the diameter. Now this one is very similar in that any line that goes through the center point, through this center point, we'll call it C again, and it gets to both edges here. So it's a line segment that goes through the center point and hits both sides of the circle. So you may be thinking, well, the radius would, either side of this, if we were to split this in half here at the center point, you could say, well, this would just be the radius, and this would also be the radius. And that's a very good thing to know, because the diameter, let's define it first. We can say diameter is a line segment passing through the center point of a circle meeting 2 points on the circle. And one thing I want to clarify real quick is that when I say on the circle, what about this point right here? Say this is A. A is not on the circle. On the circle is anything on this black line that goes around that creates the circle, the curved edge there. So anything on that would be labeled on the circle. So for a radius, it's a line segment that passes through the center point, and it meets 2 points on the circle. And they'll always be what you could describe as like straight across from each other. And if you have two radius lines like this, and they are directly across from each other in the same exact direction, no angular curve or anything like that, then that creates the diameter. But it's best, in my opinion, to think that the diameter is 2 times the radius, or the radius is the diameter divided by 2. And we will use this notation. You'll see lowercase r for radius and capital D for diameter. So keep those in mind. I guess we should go back here on this page and say R is the notation for radius, and D is the notation. We don't have to write that out in a sentence, but D is the notation for diameter, capital D. And you'll see this throughout. You may have questions that just say R equals this or D equals this, and it's good to know exactly what those are talking about, not just if it's a specific point. Let's move on to chords. Now, this is quite similar to a diameter, or the diameter. In fact, the diameter is a chord itself. It's just a special type of chord. So we can put that in the margins up here. We can say that diameter is or equals a special chord. So the diameter is a special chord, but a chord is just a line segment. We'll abbreviate segment here, where both endpoints are on the circle. So when we work with circles, there's many ways that you can envision them that may help you think these things through. For example, let's pretend that this circle we're looking at up here, let's pretend that this circle is like a pizza. And you took a pizza cutter and you just cut through it. The line segment created here, not this line that extends through, but the line segment created here, where each point lies on the edge of the circle, would be a chord. And, we can say, just for reference, that the center point is up here. So it's not through the center point. If it was, it would be the diameter. But it's not. This is just a chord that goes through. And there's things we can say about this. For example, you can kind of see that as you move further away from the center point, as this chord goes further away from the center point, it's going to get shorter. So let's make note of that. If it's further from our center point, it is going to be shorter. And then you can also say that if it's closer to the center point, it will be longer. And that makes sense if you look at it. There's less space down here as you go. If we had one down here, make sure to specify that it's not this line that goes through it. It stops on the circle. The endpoints here and here. If it's down here, that's much shorter. And of course, it's farther away. So that's something you guys may have been able to see and understand, but not necessarily realize as a property. So that is something you definitely want to keep in mind for problem solving, questions, all that stuff you will see in the future. So, clear out some space here because we're not done talking about chords. Okay. So, you may be asking yourself, well, what if, and you may not be asking yourself this, but you will be asked this at some point. So you may be wondering, how can we find the shortest distance? The shortest distance from this center point to a chord? Of course, if you went somewhere from well over here at this point, that's going to be much longer than this one right here. So how do we find that shortest distance between a center point and a chord? And the way we do that, draw our chord there. The way we do that is, you guys remember a term we've had in the past. That term is perpendicular bisector. And let's tear this apart for those of you who don't quite remember what it means, and it's okay. It's okay. We can always revisit these things. So perpendicular means any two lines that meet at a 90-degree angle. For example, like that. We'll say that's a 90-degree angle. Those lines are perpendicular. And bisector, let's think of what sector means. Sector meaning to take things into sections, and bi meaning two. So a perpendicular bisector, and you may think of angle bisector, we've used that. A perpendicular bisector would be a line that comes through and splits something exactly into two pieces and is a 90-degree angle. So let's slow down here and think about it with just two lines, the circle aside. So if we had a line here and a line coming down through, say this line ends at these two endpoints. Call this one that comes vertically as A, and this line is line B. So line A is a perpendicular bisector to line B if it creates a 90-degree angle and it splits B into two equal parts. So the shortest distance from the center point to any chord is the perpendicular bisector coming from the point to the chord. So in this case, we have this these points as A and B. We'll erase this one to stop any confusion. So if we had these two, this chord labeled AB, the points or the two sides created, they'd come down to a 90-degree angle, and those two parts created, we'll call this point in the middle C. We would know that AC is equal to AB. And we would also know that this line here, this from the center point to the chord, is perpendicular. So, it sounds like a lot, but maybe I over-explained it. But keep that in mind, that the shortest distance from any point to a chord is the perpendicular bisector. So let's think about some more stuff relating to chords and how what we just learned could be useful. Well, here's one bit of information. Any two chords of the same distance or of equal distance from the center point, and we'll abbreviate center point here to just CPT, center point, have the same length. One second here, some technical difficulties. Have the same length. So let's look at what we have over here. Let's say you have another chord coming here. And let's say that this line, they're both the same distance from the center point. We'll call this one DC. Well, then we know, since these are the same distance from the center point, that line AB is going to be congruent to line DC. So think about that. Think about how that makes sense. Because we said earlier, the further you get away from the center point of the chord, the shorter it is, and the closer you are, the longer it is. But if you're the same, the lines are the same. And we'll do a problem about that here in just a moment. But we want to talk about one other thing first: the circumference. The circumference is the distance around a circle. And we'll use a little arrow here to kind of explain this. The distance around the circle. There actually is something a little bit relative to this in an upcoming activity. So if you ever see an arrow around a circle, try to think circumference. So the area or the arrow around the circle, or the distance around the circle. The distance around the circle. Think about it if you made like a small cut in the bottom of the circle, let's say right here, and just unrolled it into a line and then measured that line. That's what the circumference is. But instead of having to do all that work, we have a nice little formula that allows us to do that without all of the extra work. And that distance, or that formula, would be the circumference, we use capital C, would equal pi, that number pi, roughly 3.14159 and so on, times the radius of the circle, lowercase r, remember that, squared. So if we wanted to get the circumference of this circle, all we would need is the radius. And you'll be in situations in class sometimes with activities where you can just pull out a ruler. Sorry about that, cannot speak. And then you can say, oh, well, this is 5 inches. Well, then, okay. Well, if we know that r is equal to 5 inches, then all you have to do is say, well, pi times 5 squared will equal your circumference. And then you can, do it out to 25. Pi equals your circumference. And then you can put that in a calculator and get some decimal. But a lot of the times, if you can get here, you'll be okay. But make sure you read the instructions thoroughly. So the circumference, once again, we review, is the distance around the circle. We denote the circumference with a capital C. and we say the circumference is equal to pi, that number pi, 3.14 roughly, times the radius of the circle squared. This is very important, very important. This is something we will be using a lot. So make sure not to just write this down in your notes, but commit this to memory. This is important. So let's do a little bit of actual math work here. So this one says, find the circumference of this circle. And we'll say, given that r equals 12. What was that formula again? We know we had the c for circumference and something to do with pi, and we use r squared, right? C equals pi times r squared. So in this case, c would equal pi times 12 squared. Right? Is this making sense? Think about this before we do any more work. Think about how this formula works, how you plug it in. And then once you figure that out, the structure, we can do a little bit more math and say that c equals pi times 144, because that is what 12 squared is equal to. And then you can rearrange it a little bit more pretty to say c equals 144 pi. And you can obviously multiply that out and get a decimal, but like I said, this is more precise than a decimal would ever be. So you want to leave your answer there on most things, but once again, remember to read instructions on any assignments. So let's look at this. Let's try to analyze this picture and see what we have. It looks like we have two chords, AB and CD, and it looks like they have an equal distance from both of those to the center point of 9, and they are perpendicular there. So let's think about what all that means put together. We have chords that are equidistant from the center point, and that is done by a perpendicular bisector. So, what exactly does that mean for us? What can we do? Let's read the problem. AB equals 8x plus 12, and DE equals 78 minus 3x. Solve for x. Well, how can we solve for x? Well, if we know these things that we've just talked about, you would know that in this case, well, I guess we could write it out a little differently here. We could say AB is equal to, or congruent to is the way to say that, DC. And if you know that's true, it's as simple as 8x plus 12 equals 78 minus 3x. And then you guys can do some adjustments here to solve for x, like adding your 3, plus 12 equals 78. Then you can say, let's scroll down here some. There we go. We can subtract the 12 from both sides. You would have 11x equals 66. And then you want to get rid of that 11 by dividing, because it's multiplied by that x. What you're left with is x equals 6. And then if you wanted to go further, you could plug that 6 into either of these functions up here. If it'll quit scrolling me back down. Either of these functions and get the distance for those lines. This is very important. This sort of stuff is something you'll see a lot. I hope that what we went through today helped. This is all quite important, as you can tell. We only went over like 3 or 4 new vocabulary terms, but they're vital in this unit. So make sure you rewatch anything you needed to watch, all that good stuff. I hope this helped. If you have any questions, leave a private comment, all that good stuff. Get your note sheet filled out. Rewatch the video to get that filled out if you didn't do it while you were doing it, all that good stuff. And be ready for the next video. Thanks, guys.